Let's continue looking more at R, our correlation coefficient. So in this case, if we see we had two data points, U, in this case, is not a horizontal line, right? Do they both lie on the line perfectly? Well, yes. So this would be an example where R is equal to 1. So anytime you have 2 points that don't form a horizontal line, R is going to be equal to 1. Now, in this case, also, everything lies perfectly on the line, and you also have a perfect relationship of R is equal to 1. So both of these have the same correlation coefficient of R equals 1. They both lie perfectly on the line. But this question we could ask is, which of these is a more convincing linear relationship? So which one of these do you think is maybe just due to random chance that there's a linear relationship right now? And which one are you like, a little more convinced? Linear relationship. Hopefully we're thinking this guy right here, right? This one seems to convince you a little bit more than that one did, that there is a linear relationship. Now, in general, this is going to be a question that we'd like to ask of how do we figure this out? So how can we tell if the strength of our correlation coefficient is actually significant? Here, I would argue that even though R equals 1, it looks like there's a perfect linear relationship. That's not a significant linear relationship. I'm not convinced at all that there is a linear relationship. I need more data at that point. So how do we tell if the strength is significant, if this R value really is something meaningful and it's not just due to random chance that we just happen to have a good high R value? Hypothesis testing, right? Hypothesis testing allows us to use statistics to judge claims based off of, is this due to random chance or is there something else going on? Is there indeed something significant taking place? So hypothesis testing should be our go-to example. So some notation that we have here. R, I already mentioned, this is just related to the sample correlation coefficient. But rho, this is the Greek letter rho, by the way. So this is RHO, rho. It's like a sassy P with a little bit of a tail there. It's the population correlation coefficient. So remember, when we make our hypotheses, then we always have to use population parameters. We're never allowed to make hypotheses with the sample statistics. So in this case, both of our null hypotheses and our alternative hypotheses will be about rho. So if we think about what the null hypothesis would say, normally the null hypothesis we're saying, what if there is no difference, or what if there is no relationship? What if there is nothing going on here? So if we think about the correlation coefficient, when there's no linear relationship, that means that it's going to be close to 0. So indeed, the null hypothesis will always be rho is equal to 0. And then the alternative hypothesis says, but wait, what if there is a significant difference? What if there is indeed some relationship, some linear relationship? Well, then we're going to say that rho is not equal to 0. Now, this is always going to be your hypotheses when you're doing your hypothesis testing on the correlation coefficient. So when you have your scatter plot, you find your line of best fit, you have all of that fun stuff, we now would like to test the claim if there is a significant linear relationship present. So we do this with our hypotheses. So then as an application of this, if we do know from our hypothesis testing, we are convinced that there is a significant linear relationship. So if R is significant, then we can use the least squares regression line for meaningful approximations. However, if based off our hypothesis testing, R is not significant, we are not convinced that there is a significant linear relationship, we should not use the line of regression for approximating. So this is one of the big differences, that maybe if you have seen linear approximations or line of best fits before, you may have done approximations and said, woo, everything works, it's great. But with statistics now, we can say, if there's no linear relationship, why would I expect this line to give me good approximations? Right? If all of my data is just completely chaotic, but algebraically I can always calculate the line of best fit is like this, why would I trust that? Why would I trust anything from this? So indeed, if we don't have a significant relationship, we don't trust the line of regression for approximating. So we should not be using it for that purpose. So then thinking back to when we talked about interpolation and extrapolation, this ties in with this as well, that even if R is not, so if R is not significant and we're doing interpolation, we shouldn't trust it anyways. So interpolation isn't always the thing that we can trust. If R is not significant, interpolation doesn't matter. But if we're doing extrapolation, we shouldn't trust our approximations either. So if R is not significant, we shouldn't trust our approximations from the line of best fit. And if we're doing extrapolations, we also shouldn't trust the results. But if you're doing interpolation, so if you're within the realm of the data and you have a significant R value, then by all means, you trust all of the approximations that you get from the linear approximation method that you've done with your linear regression line.